That's what I was thinking. I was like,
Wait, I thought it was
I thought it was A, but like at the same time, I feel like that is really easy.
All right. Well, let's think about it because we might have the right idea. We might be underthinking, might be overthinking here. So let's think about what's going on. We are looking for a value of x on this interval where our function a takes its minimum value, basically saying at what value of x do we get a minimum on this closed interval. So a minimum on a closed interval, extreme value theorem. We want to think extrema on a closed interval is actually screaming at us to think extreme value theorem. We want to know on this interval, when are we going to have our not largest, but when are we going to have our smallest output? And you might be able to think through this just understanding this function right here, but in a different context, maybe the function would be a little bit more difficult to understand. What we would do if we were trying to apply the extreme value theorem is we would look for the critical values. I would take the derivative of my function, which in this case would be x squared plus x to the fourth plus x to the sixth power, and see when does this equal 0, when does this not exist. I would look for my critical values when my derivative of this function equals 0, and this thing will equal 0 at
0.
X equals 0, and then it's just going to be increasing after that because it's very, very positive. Is it ever going to not exist?
No.
No, okay? So on the interval, we have no critical values. So that made this one a little bit more convenient. But if we did have critical values on the interval, we would have to worry about those as well. Because now the only values we have to worry about are endpoints. We're looking to see which one gives us the smaller output, 1 or 50. And as you can probably reason through, since this function right here is positive for all values between 1 and 50, 1 is going to give us the smaller output rather than 50. So yes, A equals 1 is the correct answer. And it might have been for similar reasons, but I do want us to be careful because the intention of this problem, I didn't write it, I found it, but the intention of this problem is to think about the extreme value theorem and see how that can apply to a situation like this. And if there was a critical number on that interval, we would have had to worry about that as well. Thoughts about that? Okay. All right. Well, also, any questions about the first two? So remember yesterday we talked about a very important thing, our net change theorem. Very exciting is our net change theorem. And just an incredible application of our definite integral, being able to accumulate all of the change in something to find out the total amount that had changed. Very neat, very neat. I want to look at one more thing related to our net change theorem. We didn't quite get to this very last thing related to our net change theorem. And then after that, we'll see where we are. But this is the last thing in chapter 4, lesson 4. It's still related to our net change theorem. Let's see if I can find, yes. All right, now there's a lot of stuff going on here. But if you're the note-taking kind, you probably don't want to write down all of this, but let's talk about it. So let's think in the way the book explains it. I'm just going to go along with it. Let's think about the velocity of a particle. And this is a pretty common situation that they present on the AP exam and stuff like that, college level calculus, is think about a particle on a number line. Particle starts at some point, let's just say it starts at 0 for convenience, and when the velocity is positive, the particle goes to the right And when its velocity is negative, the particle goes to the left. So we have a speed, and we also have a direction, whether it's positive or negative. It's moving back and forth on this number line. Well, there are two things that we could talk about. And this is also true when it comes to driving your car and doing stuff like that. So we can make up some problems related to those things because we always like to talk about rates when it comes to cars. If we take, again, velocity being a rate of change, if we integrate the velocity as it is, we do our normal thing, we integrate the rate of change where the velocity could be positive, it could be negative. If we integrate that and find its total change, we are going to find what we call its displacement. Where is it in context from where it started? It went some positives, it went some negatives, it went some positives, went some negatives, and then where did it end up after all of that? Visually, it would look kind of like this graph right here. Imagine our particle starts at time A, and because we have our velocity is positive, during all of this time right here, it's accumulating, moving to the right. And then in this region right here, for all of these outputs, our velocity is negative, so it's moving to the left. It went back a little bit to the left. It's gone more to the right than to the left, so right now it's still to the right of where it started, but then it went to the right some more. And as we know, our definite integral does, as we know when we accumulate functions, the negative cancels out with some of the positive. And so this is giving us, because it's moved more to the right than to the left, we know our final position is going to be a little bit to the right of where it started. We call that displacement, right? How far were we displaced from where we originally went? It's still going to be a positive or a negative, which is still going to tell us how far to the right or how far to the left of where we started. Displacement. We also might be asked, where is it? What was the total distance that this particle traveled? Right? Because if we go to the right and we go to the left and we go to the right again, we've traveled more than what our displacement is telling us, because going to the left is still distance we've traveled, and we don't want this down here to necessarily cancel out with what we've already had. Because again, total distance traveled, we want to accumulate all of that. Think about when you're driving your car, if you've ever looked at the odometer, every mile you drive, it keeps ticking away, increasing and increasing until one day your engine dies, right? It's adding it up. And so when you drive to school and when you drive home, your displacement is zero, right? You are in the same, your car is parked in the same place that it began, but the total distance traveled, there was a total distance traveled. Your odometer has increased. There is a change, and your total distance traveled is still marked on your odometer. There's the difference. And how we deal with that, if we want to find the total distance traveled, we want to take the absolute value of our velocity. We want our velocity to always be positive. This stuff down here, if we take the absolute value of our velocity, it's going to it would look like that now. And instead of having that negative A2, it's now going to be a positive right there. So it's going to be accumulating all of our regions as positive distance traveled. And so our total distance traveled is usually going to be more than our displacement. They would be the same if our velocity was always positive already, but there. Now when it comes to this, probably 99% of the time, if we need to find total distance traveled, it is just a difference of typing it in our calculator this way. maybe 99 is an extreme. There are situations where, and we can look at them, where I can remember looking at practice tests or mock exams, where we have to look at the graph in our calculator, or we have to do something where we can, but most of the time it is just typing in our calculator with the absolute value symbols. Because if you didn't know, when you're typing something in your calculator, if you want to do absolute value symbols, you can go to math and you can go over 1 to number, and you can actually select absolute value. Type that in your calculator. All right, big difference right there. Easy to get them confused. Displacement, total distance traveled. I think if they make sense if you think about it. All right, let's take a look at this one right here. So again, we have a velocity of a particle moving along the line is given by this velocity, where of course time is in seconds, and we want to find the displacement of the particle on the interval from 1 to 5. So to find the displacement, all we have to do is integrate from 1 to 5 our velocity function. So t cubed minus 10t squared plus 29t minus 20 dt. Again, setting it up with that dt at the end from 1 to 5. If this is on the AP exam, you're already getting a point from just that setup. To save ourselves, I know we could work this out. We could do with some fractions. It would be a ton of fun. We always have fun with that. But let's just type it in, because most likely these applied integrals, especially on the free response portion, this is the kind of stuff they allow you to have your calculator with.
Wait, why is that? Then you just
Because I mean, think about this. I mean, you're dealing with a bunch of 1/3s, and you're dealing with a bunch of fractions, and ultimately, they don't want to test your math, algebra. Well, they don't want to teach your, not teach. They don't want to assess as much of how good are they at adding fractions. They want to see how much calculus you can do.
for this, can we just put equal to the answer, or do we?
If this was calculator allowed, AP exam, they want boom. They want that right there. This is your work. If it's calculator allowed, that is your work right there.
So we don't
Equals.
Untitled.
You would not have to do that if this is calculator allowed. And the thing is when you're given the calculator, they're gonna most of the time make that function so stupid crazy. You saw that one yesterday that we had from one of those past AP exams. They make it where you wouldn't even begin attempting it. Like they want you to be able to use your calculator to do that. They would give you a point for that setup, and they would probably give you a point for the 32/3 and the units. They definitely want to see units. So they assess the units differently depending on how many problems have units on the thing. If there are, for a free response question, there's usually 4 parts, A, B, C, D. If 2 of the parts have units, then a lot of times there'd be 1 total point for the question if you got both the units right. So you don't want to, those little things add up to points. And if you set this up wrong and you wrote that number wrong, but you still put the units, you might be getting a point. Because, I mean, nowhere in this question does it say, how many feet did it travel or something? It is understanding the displacement of a particle when it's in feet per second. Is talking about how many feet away from where it started was. Still putting feet there is part of our understanding of not just this problem, but the calculus behind it. So they do care about that for sure. Now, the total distance traveled, it can be as simple as writing this and typing into our calculator pretty much the same thing we did before, but with absolute value symbols around it. Because our function, our velocity function, has been referred to as v of t, you can write that on your AP exam, just write that on your paper. If you don't want to write this all out, of course you still need to type it all in so your calculator knows what it is. And if we do that,
That's so smart. That's how you find it. Huh?
Calculators?
No. That's the notation to find displacement. I wouldn't have thought of it.
What?
Oh,
You
know what I mean? Like,
integral?
the absolute value
That's for
of
total
function.
distance.
Huh?
It's for
I
total
mean, yes,
distance.
that's kind of
okay, and
I wish we were in the 18th century or something.
and for this I got
Maybe
71
you. I do not want to be in the 18th century.
over 6 feet. So there could be a situation where we have a much simpler velocity function. Let's just see if I can make one up real quick. Let's say our velocity function was x squared plus, minus 2x. Yeah, that sounds good. Okay, look at that. No, let's make it t's, all right, because that makes more sense. T squared minus 2t. All right, this right here, what we're about to do right here, this could be an example of one they could give you on the non-calculator multiple choice section. This is what I would expect. Of course, if we wanted to find the displacement from 1 to 5, we would just integrate v of t, right? It's just, okay, that would be because displacement, you're just integrating the velocity over the time interval. But let's look at the second question. What if we wanted to find the total distance traveled by a particle represented by that velocity on the interval from 1 to 5? We don't have our calculator to just do the absolute value. What do we do? Well, we know that we would have to integrate, and we need our velocity to always be positive. So you could do it a few different ways. You could do a little sketch, okay? A little sketch real quick. You could start plugging in values, especially those values between 1 and 5, because that's where we really need to know what it looks like. If we plug in a 1, is this going to do what I wanted it to? Yes, it'll be good. Okay, this will be good. When we plug in a 1, we get out a -1. When we plug in a 2, come on, yeah, when we plug in a 2, we get out a 0. All right, so it's looking for that nice value right there. When we plug in a 3, we now start getting out positive values. That's what we should realize right here. We start getting out positive values for all those values until we get to 5, which is somewhere up here. We know it's a quadratic, so it really looks more like this. That's kind of what our function looks like. I can see kind of quickly right there, and the other way that we could do this is to just set it equal to 0 and find when it changes. When is it going from, when is it below 0, when is it above 0? And because it is below 0 from 1 to 2, I need to make sure that that value is positive. So I can integrate from 1 to 2 of this t squared minus 2t dt. And when I get this answer, which I know is going to be negative, I just make it positive. And then I also integrate from 2 to 5 of t squared minus 2t dt. And I know that's going to be positive, and I add those two values, and I make that first one positive to make sure I'm getting my total distance traveled. That is pretty realistic for non-calculator, because solving and finding where it changes from being below to above the x-axis is not a giant stretch of our imagination. We could sketch the graph really quick. There's kind of a few different ways that we could get a better context of that without having to do some crazy algebra stuff or some crazy numeric stuff. There's some light stuff to understand what's going on, although it does make it a trickier problem, and then it's all related back to being able to apply our calculus. So, other than something like that, I would expect it to be very calculator friendly. All right, thoughts, questions on this? Okay, would you like? Is this something we like to see a practice problem on, or do we feel all right?
Practice problem.
Yeah.
Practice problem. All right. Do I have
Calc
one?
or no calc?
You want what?
That's them doing on calculator or no calc?
No calculator.
No calculator. All right. Let's.
What? He's like that. We're gonna get to that.
Why do you want to be in the 18th century?
We could have came up with stuff.
Let's just be honest. If we were in the 18th century, I would not be sitting in this class right now.
Neither would I. Neither would you.
Yeah.
None of us
We would all not be here.
You know, like, it was 1700, right?
Sucks. I'd be the only one here.
You
Oh, man.
I'm a woman.
I'm black. You're Indian.
Okay, so.
I
I mean, he'd still be teaching an empty classroom then, I guess.
1950, I guess.
Landon, you know, he wouldn't be here.
No? It was like 19th century.
Landon
maybe.
would be.
18th century would have came, they would have made him work in the railroad, right?
That would be
That
more
was
19th
19th
century, but yeah.
Maybe like 1970s.
When did I come?
I don't know when I came there.
More like 20th century.
21st.
21st century.
We were a little late. We had our own problems to deal with.
Yeah.
Dude, we were ruled by the British too.
I was here, but I wouldn't be here.
What would you be doing?
Cleaning a house, raising kids.
Wait, at your age? What
Now
did
you get to do that and a child.
Yep.
I'll be back home.
Wait.
I never died.
Did Nigeria ever have problems?
Of course, but I guess my bloodline never got caught.
Really?
Well, I migrated here. I don't know nothing about bloodline. I guess I know.
So, can we all agree not to go back to the 18th century? I think we
It could
agree.
be different though.
Huh?
It could make a change.
It
I
could be
don't think
different.
so.
I don't know how that would work.
Until like 19th century.
Look at that.
Did
Okay.
you just like come up with this question?
This one right here, yeah.
What is yada yada?
I don't want to say all that stuff that we've been saying. This is a particle that's moving on a number line, back to the left or the right. That kind of setup stuff based on that velocity.
Just so I don't get confused, can you write all of that out for me?
Nope.
Nope.
Do we have any units?
Yeah, we should do units for sure. Let's say velocities and, we'll just say units per minute, because we're kind of just talking, well, in this case,
Okay.
I'm just talking about like units on
Yeah.
coordinate plane.
tried to find where, like, for this problem, no calculator, trying to find, like, when you graphed it, you did that to see where it crossed the, where it became negative, so you know how you want to set up your lower and upper bound. So you suggest just graphing it every time to see?
Graphing makes sense, or you could set it equal to 0, find where it equals 0, and then think about, okay, to the left of that, is it positive or negative?
Okay.
And that can just kind of give you even if it's not visual, I mean, you know, and if it's a quadratic, it doesn't have to be perfect, you know, like our last one. If it's doing a bunch of this, then you can just kind of find where it equals 0 and then find around it, you know, kind of like what we did for a derivative to find when it was increasing or decreasing. Just get a sense of what's going on. On this last one, and we didn't have a lot of time to look at it, but essentially we have an initial value, and then we want to see all of the change that has occurred. And so it started at negative 11. We want to add all of well, I mean, if it's saying where is the particle, we want to take all that displacement and add it to it. If it moved to the left, adding a negative is going to magically move it to the left. If it's positive, it's going to move to the right. But from 0 to 8, what was the displacement? It was 0. It's actually 0, because there's as much above and below. Anyways, so the displacement is actually 0, so at t equals 8, it'd actually still be at negative 11. It did move to the right, it then moved back to the left, and it finished where it started. So that's another way they can ask these kind of things, is accumulating all that change to find out where's the particle now. So that is, like I said, that's all the stuff from chapter 4, lesson 4. That is so